Good morning, everyone, and thank you for attending this session. I am Julien Soulé, a PhD student at University Grenoble Alpes and Thales Learn Earth System. Today, I present our recent work on streamlining resilient autoscaling in Kubernetes using multi-agent reinforcement learning. This work is part of a broader effort to bring explainability, robustness, and automation to auto-scaling processes, especially under adversarial or unexpected conditions. We propose a framework which is called Karma, standing for Kubernetes Autoscaling using reinforcement learning and multi-agent design. The goal is to go beyond reactive threshold-based methods and to treat autoscaling as a coordinated, intelligent decision-making process among multiple specialized agents. So let's begin with the motivation. Kubernetes is widely used for managing containerized applications. However, its autoscaling capabilities, especially the default horizontal pod autoscaler, are limited. These mechanisms rely on simple reactive rules that just replica based on CPU or memory thresholds. But in practice, cloud environments face a variety of failure types. We may have DDoS attacks that float ingress points, misconfigured port that crashes in loop, or services that overconsume resources, starving others. These are complex and often concurrent failure scenarios. Now imagine trying to handle all of that with a single metric and no coordination. Even reinforcement learning based autoscaler, for short, they often optimize latency alone and ignore this multi-failure dynamics. What we truly need is a resilient adaptive system that understands roles, responsibilities, and missions so that agents can respond appropriately and collaboratively. That's the gap we aim to address with Karma. To ground our work, we conducted a review of existing solutions. On this table, we compare popular autoscaling systems across several dimensions: support for adversarial context, learning capabilities, real-world deployability, explainability, and multi-agent coordination. Some systems, like GIM HPA, provide flexible learning environments but lack deployment support. Aware consider multiple QoS objectives but is not fully automated and does not use multi-agent setups. Others, like Air Late Core or COPA, focus on adaptation but fail to offer safety guarantees or explainability. In contrast, Karma aims to bridge all these gaps by combining multi-agent learning, digital twin modeling, and structured organizational constraints. This combination lets us train policies that are not only efficient but interpretable and robust. Karma is a four-phase framework designed to support continuous, resilient autoscaling. It starts with modeling, where we build a simulation, a digital twin of the real Kubernetes cluster. Then, in the training phase, we use constrained multi-agent reinforcement learning to produce specialized autoscaling policies. The third phase, analyzing, is where we post-process agent behaviors to infer the roles they have actually played. This helps us verify that what was learned is both interpretable and aligned with our design. Finally, in the transfer phase, we deploy the train agents in a real cluster and close the loop. Real data updates the digital twin and the cycle can repeat. This design supports adaptive, explainable, and robust policy deployment in dynamic cloud environments. In the modeling phase, we construct a digital replica of the Kubernetes cluster. We collect traces of observations and actions from the real environment, like scaling events, port statuses, traffic metrics, and so on. And we use them to approximate a transition model. The environment is modeled as a zero-sum stochastic game between an attacker and defenders. This is essential. By simulating adversarial behaviors, we can train agents that proactively anticipate and resist disruptions. Unknown transitions are approximated using a neural network, typically a multi-layer perception, so that the system remains general and scalable. This model phase allows for safe and accelerated training without jeopardizing production workloads. Once the environment is modeled, we move to training. Here we use MAPO, multi-agent proximal policy optimization. For joint learning, each agent is assigned a role, such as DDoS mitigator or bottleneck resolver. To guide the learning, we impose two types of constraints. RAG or role action guides restrict which actions an agent can take in a given context. GRG or goal reward guides influence learning by shaping the rewards towards the mission goal. This constraint can be hard, fully enforced, or soft, used to bias the learning. This approach builds on prior work, Moise plus Small, presented at AMAS 2025, which integrates organizational models into multi-agent reinforcement learning. The result is a set of specialized coordinated policies that align with high-level mission goals. After training, we don't just deploy blindly. In phase 3, we conduct a post-hoc analysis of the agent's behaviors to assess if the organizational structure was respected. We analyze trajectories of actions and observations, including using clustering techniques. For actions, we look for repeated behaviors patterns using methods like dynamic time wrapping or longest common sequence. This helps us infer implicit roles. For observations, we track which goals are typically achieved, allowing us to infer missions. These introspections let us validate that the system learned was what we intended and give us a way to document our debug behavior when needed. In the final phase, the train agents are deployed in the real Kubernetes cluster. Each agent monitors metrics in real time and decides when and how to scale its assigned service. The agent interacts with Kubernetes via API call, adjusting replica count on the fly. We also maintain the digital twin, which continues collecting data and can be periodically retrained to adapt changes. This approach ensures that the system remains resilient and reactive, even as the environment evolves. And importantly, it allows operators to benefit from structured, explainable decision making at runtime, something that traditional autoscalers do not offer. To evaluate karma, we built a simulated Kubernetes cluster with 4 interconnected microservices forming a pipeline. This service is receives requests at one end and process them step by step, creating dependencies and bottlenecks. We inject failure conditions like DDoS attacks and prod crashes and misconfigurations. Each agent controls a single service and learns how to scale replicas based on its local view and role. The simulation environment is fast and fully instrumented, allowing us to evaluate multiple baselines and variants over many runs. We compare Karma to standard methods and to updated version of our own framework. This table summarizes the performance of all approaches under standard operating conditions. We measure success rate, latency compliance, and pending requests. Karma clearly outperforms all baselines. It achieves over 90% success rate, maintains low latency, and keeps pending requests below 6%. In contrast, traditional autoscalers like KHPA struggle with dynamic load, and even advanced systems like Aware or Airlit Core fail to match Karma's coordination. These results demonstrate the value of multi-agent coordination and of role-guided learning. Now let's let's look at learning dynamics. These curves show the average reward over training episodes for different system variants. We see that karma converges faster and more stably than others. Systems without constraints suffer from high variance and delayed learning. Single agent setups fail to coordinate actions and often create resource contention. These curves provide quantitative evidence that structured training with roles and missions not only improves final performance, it also improves training efficiency and reliability. A major goal of Karma is not just performance but explainability. Here we show the communication and authority graphs among roles. Using our analysis tool, we can match observed behavior to expect rules and verify structural consistency. The inferred rule aligned well with predefined responsibilities. This level of post-hoc analysis gives us a way to audit and debug agents' decisions. It also opens the door to generating natural language explanations of system behaviors, something we plan to explore in future work. We also perform ablation studies to understand the contribution of each element. Removing the digital twin leads to slower training and worse generalization. Using a single agent model increases latency and reduces success rates. Omitting organizational constraints leads to erratic policies and coordination failures. These results confirm that each part of karma, modeling, multi-reinforcement learning, and Moise plus more adds significant value. The system as a whole is more than the sum of its parts. To summarize, Karma is a resilient, structured, and explainable framework for Kubernetes autoscaling. It integrates multi-agent learning with organizational constraints and digital twin modeling. It outperforms existing methods on success rates, availability, and training stability. In future work, we plan to extend Karma to multi-node cluster and to integrate streaming services or time-sensitive constraints. We also exploring how large language model could be used to synthesize documentation from the learned agents policies, improving transparency and trust. So thank you very much for your attention. The code and database are available on GitHub, and I'd be happy to take any questions from my email.